So we are going to discuss exponential growth and exponential decay. So what does it mean by a quantity is growing exponentially? It means that it is following some kind of an exponential function. So growing exponentially means the function will follow something of this sort. So this is the graph of e to the x, and if k is greater than 0, this is roughly how the graph will look like. So there will be an exponential growth in that sense. Similarly, if k is less than 0, then you will see the graph will look like that. In particular, e to the power minus x is a graph which looks like this. And in this case, we'll have an exponential. It is decreasing like an exponential function, like a decreasing exponential function. So this phenomena is called exponential decay. Yeah. Decay means to basically, in some sense, one meaning of decay is to become smaller and smaller and eventually disappear. So in general, it is given by q equals to a e to the power kt, where a and k are some constants. So this is how a quantity is given when you have an exponential growth or decay. Now let's take derivative on both sides of this function with respect to t and see what do we get. We get dq by dt is a times constant comes out, derivative of e to the power kt is e to the power kt multiplied by d by dt of kt, chain rule. That is going to be a e to the power kt times k. This is your q, right? So I can also write it as q. So what do we get? We get dq by dt is kq. Now there is another way to look at this equation, right? You can see this is called the rate of change of q, right? So we can say rate of change of q, rate of change of q. Now it is some constant times q, right? So rate of change of q is proportional by constant. Is proportional to what? To q, isn't it? So this is the setup. So now if you're given other way around, if you're given say dq by dt equals to kq, so given dq by dt equals to kq, the solution, now you can go other way around too. You can go back and say, well, if you're given this, what is the solution? What is q? Q will be a e to the power kt. So in this case, given this, the solution to this equation. This kind of equation which have derivative inside them are called differential equation. In our course, we will only restrict to a very special kind. All right. So solution is of form q equals to a e to the power kt. Instead of q, if I write y, then I get what? I'll get y equals to a e to the power kt. Now sometimes this a is a constant, right? We don't know. But what if you're given more information about y? So you're given information about y, say y of 0 is y naught. Then you plug this instead of y, if instead of t you plug, so you can think about this as y of t. So instead of t, if you plug 0, what do you get? You get y of 0 on one hand is a e to the power 0, which is a. and on the other hand, you're given that that is equal to y0. So therefore, you can change your solution now to yt equals to y0 e to the power kt. So since you're given the value of y at some point, this is called initial value problem. So let's read the following problem. So Calculopolis has a population of 25,000 in 1970 and population of 30,000 in 1980. Okay. What population can the Calculopolis planners expect in year 2010 if the population grows at the rate proportional to its size? So you see, the last line is the key, some sense. So let give a name to the variable. So let P of t be population at time t. Yeah. Now, first of all, so you have to decide either you can take t equals to 0 as 0 AD, or you can say, well, starting from what? So where t is measured, it will give you the same answer though, measured from 1970. What does it mean? It means that is t equals to 0 at 1970, t equals to 10 at what, 1980, and you have t equals to 40, means you are at 2010. Okay. Yeah. So because that is the starting point of this. Now you can say, well, why didn't we start with t equals to 1970 at 1970? You can do that too. The solution will be the same. Now, what is given to us? The population grows. So rate of change of population is dp by dt. And it is proportional to its size. That means it's basically some p times k, where k is a constant of proportionality. K is a constant of proportionality. So now we already know what is the solution to this. So solution to this is given by, the solution is what? Solution to this problem is P of t equals to P0 e to the power kt. What is my P0 given to me? So P0, population at time t equals to 0. So P of 0 is P0, which is given to me as what? 25,000. So this is going to be 25,000 times e to the power kt. So this is your population at time t. Now, if you look at this problem, you need to basically find out. So you're given, you're given P of 10. So P of 10 is 30,000. And P of 40 is the question mark, right? This is what we need to find out. Now, we could have plugged 40 in this equation right away, but the problem is that there is a k, constant k, which we need to find out. So let's find out that constant k. So what do we get? We have P of, so now to find out k, notice the following. What is P of 10? P of 10 on one hand is 30,000. And on the other hand, if you put 10 in the formula, you get 25000 times e to the power kt. And from here we can solve for k. So divide 25,000 on the other side you get e to the power kt. And sorry, we have to put t equals to what? 10 here, right? Because t is 10. So what do we get out of this? So this is going to be, so 6, so 25,000. So if you divide both top and bottom, you'll get 30 by 25, which is same as 6 by 5 equals to e to the power 10k. Or k equals to, or from here you can find out k equals to ln of 6 by 5 divided by 10. So now you got to this as an answer. Now what? Now we need to basically find P of 40. So P of 40, if you put it in the formula, so either I plug this K back into this formula, right? I should plug this K back, or notice the following. What is P of 40? So P of 40 is e to the power K times 40. Now this can be written as e to the power 10k, the whole power 4, right? Because the powers get, these gets multiplied, right? So now instead of going to substitute this for k, I will substitute e to the power 10k, because I don't have access to calculator for the exam. So I'm going to basically substitute, instead of e to the power 10k, I'm going to substitute 6 by 5. So I get 25,000 times 6 by 5 to the power 4. Okay. And you can leave it that. This is calculator ready format. Are there any questions, comments so far? If you have a radioactive material, the radioactive material is known to decay at the rate proportional to the amount present. This means if n is the amount of mass of radioactive material present at time t, then it must satisfy the model dn by dt equals to minus kn, where k is greater than 0. So again, in this case, what will be the solution? The solution will be of form, you can check, n of t. So think about as your, this as your k, as a new k, call it big K, or call it some other number, right? Let's call this alpha. So you'll have dn by dt. So if you look at the previous equation, you can see that n equals to what? N equals to n0 e to the power alpha t, and then alpha is minus k. So we have n0 e to the power minus kt. So this is a solution to this equation. Okay. So let's look at the following. If it takes 8 days for 20% of particular radioactive material to decay to 20%. So what happens is, in 8 days, 20% of the material is gone. Yeah, of the radioactive material. How long does it take for 100 grams of material to decay to 50 grams, 40 grams, and 0 grams? So again, we have, so since we are talking about radioactive decay, we have the following. It will follow the following equation. So we have dn by dt is minus kn. This implies nt equals to a e to the power minus kt, where a is some constant. Yeah. And you can basically think about it as n0 e to the power minus kt, where what is my n0? N0 is the amount present at time t equals to 0. All right. So this is a solution. So now what is given to us? It is given to us that in 8 days, 20% of material is decayed away. So we have n of 8 is going to be 20% is gone, so 80% remains. So n of 8 is 80% of n0, which is 0.8 times n0. So this is what is given to us. And by formula, by our solution is going to be n0 e to the power minus kt. Again, what are we trying to find out? Our problem is to find out the time taken for 100 grams to decay to 50 grams, right? But first we need to have some estimate of what this K is. So this should give us, if you cancel n0 on both sides, you get 0.8 equals to e to the power minus kt. Or if you take ln on both sides, so ln of 0.8 equals to minus kt. Or this implies k equals to, so this should have been 8, right? Because we are looking at n of 8 is time t has to be replaced by 8. So this is replaced by 8. This is replaced by 8. So we get k equals to minus 1 by 8 ln of 0.8. So this is your k. Now you're asking the following question. So you have got estimate of k. Now let's answer the first question. Question 1. Start with 100 grams, right? And what do we get? At what time? So let t be the time when it decays to 50 gram. To 50 gram. So this is what we want to find out. So now note that your n of t could have be written now as what? N of t is n0 e to the power minus of minus, so it becomes what? Plus ln of 0.8 divided by 8 t. So now we start with 100 grams and now we are looking for, let t be the time when it decays to 50 gram, and we need to find out what this t is. So let's try to find that out. So perhaps it's a good idea to simplify this a bit. So let's simplify. N of t equals to n0. Now this can be seen as e to the power. You are multiplied t by 8 times 0.8. Right? Now note that this can go in the power. So this is going to be ln of 0.8 whole power t by 8. And ln and exponential, so ln and e are inverse of each other. So you get basically the n0 0.8 to the power t by 8. Okay. So now let's answer the question. So your n0 is 100. This implies n of t equals to 100 times 0.8 to the power t over 8. So we have simplified it to make it look like this now. Now question 1, reducing to 50 grams. We get what? 50 equals to 100.8 to the power t by 8. This means what? This means 0.5 equals to 0.8 to the power t by 8. Now we need a mechanism to bring the power down. So ln is the way. So take ln on both sides. So ln of 0.5 equals to ln of this, which is going to be t by 8 times ln of 0.8. And this will give us, this gives us ln of 0.8, 0.5 divided by ln of 0.8 multiplied by 8, and that is my t. And if you use your calculator, you can see that this is roughly going to be 24.85. And what is the unit of measurement? Everything was measured in days here. So this is also measured in days. Similarly for question 2, question 2, reducing to 40 grams. In that case, you can see that 40 equals to 0.8 t by 8. And you'll see everything will remain same, except instead of this 0.5, you will have 0.4. So this implies 8 ln of 0.4 divided by ln of 0.8. And that turns out to be roughly, this is your t, is 32.85 days. Now question 3, when does this become 0? So in that case, you have n of t equals to 0 times 100. This is equal to 100.8 to the power t by 8. But this can never be 0, right? Because exponential functions of these type never become 0. So, but never becomes 0. Right. So let's move to the next problem. Usually the K is specified in terms of half-life of the isotope T equals to ln2 by K. Yeah. So you see, every radioactive material is what? I mean, like, what is unique about radioactive material in this formula? The K here is unique, right? Because N0 is a starting amount, right? What is different about, say, if you take uranium or plutonium, or for that matter, carbon-14, the difference is in K, right? So the difference lies in K. So now let's derive that the half-life, if the half-life is tau, then half-life and K are related to each other by the following equation. So why is that the case? So let's look at N of T. So N of T is given by A e to the power minus kt, right? Or you can say this is N0 e to the power minus kt. Now for half-life, what happens? For half-life, you will get, so let's give it a name, tau. So for half-life, you have n tau equals to n0 by 2, right? So equating this to the equation e to the power minus k tau. So compare these two. So what do we get? We get half equals to e to the power minus k tau. Or if you take reciprocals on both sides, you'll get 2 equals to e to the power k tau. Taking ln on both sides, so you get, or writing this equation into exponential, from exponential to log, you'll get ln2 equals to k tau, or this means ln2 by k equals to tau. So this is a connection between the half-life and the exponential function. Half-life and the constant k. So the idea is, if you take a warm object and put it in cooler surrounding, its temperature will steadily decrease, right? So law of physics is known, which is known as Newton's law of cooling, tells you at how does it cools down, right? It's not like if you take a hot cup of tea outside in the snow, it will cool down instantaneously. No, that's not happening, right? It will cool down, and it also depends on the temperature of surrounding, right? If you take a hot coffee and put it in an oven which is equally hot, the coffee will not cool down. So the way an object cools down, or for that matter heats up, uh, basically depends on the temperature of the surrounding, right? So Newton's law of cooling tells you exactly how does it depends. So what does Newton's law of cooling says? It says that the rate at which the object cools down is proportional to the difference of its temperature and the surrounding temperature. Yeah. So it basically is telling you that it is proportional to the difference of temperatures between the object and the surrounding, right? And so if you want to write this in terms of a differential equation, so dt by dt will give you, so if T of T is the temperature of object at time T, the rate at which it is cooling down or heating up is proportional. So remember, this is a proportionality sign. Proportional to the difference of the temperature of T and the surrounding. So M is the temperature of the surrounding. So therefore, dt by dt is going to be K times T minus M, where K is some constant. This constant is called cooling constant. Now, this cooling constant depends on your object, right? I mean, like some objects cool much faster than the others, right? But that is not our concern. Our concern is basically to solve this equation, right? But you should look at this. It's an interesting read about cooling constants. So let's read this problem. So when a cold drink is taken from refrigerator, its temperature is 5 degrees. After 25 minutes in 20-degree room, its temperature has increased to 10 degrees. What is the temperature of drink after 50 minutes? When will its temperature be 15 degrees? Okay. So let's ask this question and try to solve it. So what do we have in this case? So we have, so let's try to reduce this problem first to something which we know. So let T minus M be Y. M is your constant. So take derivative on both sides. So what do you get? You get dt by dt equals to dy by dt. And then this differential equation transforms. So the differential equation, or the equation 1, becomes equation 1 is then given by what? Dy, instead of dt by dt, I'll write dy by dt equals to k times y. So now what did you do? You reduced your known equation, sorry, you reduced your unknown equation into something which you can solve, right? So what do we have in this case? So what is the solution to this guy? Solution is given by y equals to some constant times e to the power kt, right? So this will be the strategy while solving this problem, okay? So in this example, what do we have? We have dt by dt equals to k times T minus, what is the temperature of surrounding? The temperature of surrounding is the room, it's kept in a 20-degree room, so it's going to be T minus 20. All right. Now, is there any extra information given to us? The extra information given to us is the cold drink, when it's taken from the refrigerator, its temperature is 5 degrees. So we are given that T of 0 is 5 degrees. And what else is given to us? T of 25 is given to us as what? 10 degrees. Temperature of the surrounding is 20 degrees. Okay, so let's do the following. So let's do what we did here. We'll substitute, let y be T minus 20. So this would imply dy by dt equals to dt by dt. So I'm going to replace this. The reason why I'm replacing this is because generally I'm used to solving dy by dt equals to ky, right? So we get that. And what is the solution? So we get this, and we get dy by dt equals to ky. So this implies the solution is y equals to a e to the power kt, right? So this is a solution. However, what is my y? Now time to put back what your t is. So your y is what? From here you can see that y equals to t minus 20 equals to a e to the power kt. This implies t equals to 20 plus a e to the kt. Now there are two constants here, a and k. We need to find out those constants. So what shall we do? We will let, so t of 0 is, on one hand we get t of 0 is 5, and on the other hand it is given to us what? If we use the formula 20 plus a e to the power 5t, right? Sorry, t of 0, right? So 0. So e to the power k times 0, right? So this will give me 5 equals to 20 plus a, which gives me a equals to what? A equals to minus 15. So put this back in the equation. So you get, the equation is t equals to 20 minus 15 e to the power kt. All right. Now we need to find what our k is. So let's do that. Now the other piece of information is that t of 10, also t of 10, on one hand it is given to me as, sorry, t of 25 is 10, and on the other hand if I use the formula I get a, what do I get? I get 20 minus 15 e to the power k times 10 equals to this. So now subtract it on the other side, so you will get, what do we get? We get 10 by 20 equals to, so 10 by, sorry, you need to subtract it, so you get 10 minus 20 equals to minus 15 e to the power 10k. This gives me that minus 10 by minus 15, which is going to be 2 by 3, is e to the power 10k, or k is going to be ln of 2 by 3 divided by 10. Okay. Then what do you get? Your t of t is going to be minus 15 e to the power t by 25 times ln of 2 by 3 plus 20. Okay. Now if you want to simplify this as an exponential, you can. So this is going to be minus 15 e to the power ln of 2 by 3, the whole power t by 25 plus 20. Now exponential and log ln are inverse of each other, e and ln. So we get, this is going to be minus 15 2 by 3 t to the power, so power t by 25 plus 20. So this is your t of t. So now, so this is your function. Now first problem is t of 50. So what is t of 50? It's going to be minus 15 times 2 by 3. Instead of t, I'm going to put 50. So I get 20. This is going to be minus 15 times 2 by 3 to the power 2 plus 20, which is going to be minus 15 times 4 by 9 plus 20, which is going to be, so 15 and 15, this cancels out, so 15, so you get minus 20 by 3 plus 20, which is going to be 60, so 40 divided by 3, which is roughly 13.3 degrees Celsius. Now the next question is about, let's look at what is the next question telling you. When will the temperature be 15 degrees? So let's call that, so T of question mark is 15. So what do we get? We get for that T, so we have 15 equals to minus 15, 2 by 3, T to the power 25 plus 20. And now we need to solve for T. So subtract, we get minus 5 equals to minus 15, 2 by 3 to the power T by 5. So this implies 1 by 3 equals to 2 by 3 to the power T by 5. So now you need to solve for T. So take ln on both sides. So this will give me ln of 1 by 3 equals to T by 5 times ln of 2 by 3. And if you multiply it on the other side, you get 25 . So this is T by 25. So you get 25 times ln of 1 by 3 divided by ln of 2 by 3, and that is equal to your T. Yeah, and then it turns out, if we do the simplification, turn out to be 67.74, and it's measured in minutes. So now, if if A0 is the amount of money invested at time at interest rate R, let AT be the amount after time, after T years, then the formula is given by AT is A0 1 plus R to the power T. Now if you compound it n times per year, then the formula becomes what? The rate becomes R by n, right? You can think about the rate basically getting distributed over this n periods per year. So you get R by n, but you need, now you're compounding by T. And then the formula for continuous compounding is AT is A0 e to the power RT. Now, why is that the case? Let's look at the limit as, so what does AT, continuous compounding means you're compounding every instant, right? So you are basically looking at n goes to infinity of, so you're compounding every time, every instance. So you have AT, this is going to be, and you're using what? N times a year. So limit as n goes to infinity, A0 1 plus R by n to the power nt, right? So I'm going to write it as n by R multiply and divide by R. So now you can bring in your n inside, n goes to infinity inside, you will see this is going to be A0 limit as n goes to infinity 1 plus R by n to the power n by R, the whole power RT. Now, what we'll do is the following. We will take R by n equals to x and compute this limit separately. So what do we get? If R by n equals to x, if n goes to infinity, x goes to what? 0, right? Because it's 1 over n. If n goes to infinity, R by n will go to 0. So this limit can be transformed into a0 limit as x goes to 0, 1 plus 1 by x to the power. Now, if r by n is x, reciprocal of that is n by r. So this implies n by r equals to 1 is equal to x. So we get 1 over x here. So n by r is, so we took r by n equals to x. So n by r is going to be 1 over x. So we get x to the power 1 over x, the whole power rt. Now this, we have already said earlier that this limit is going to be what? E. So we get a0, inside is e to the power rt. So let's look at this. So you can also think about this as a solution to differential equation. dA by dt is RA, right? For the continuous compounding. So you can think about this as a solution to the continuous compounding. Let's look at the following. That $100 is borrowed at 19% interest. Find the rate at the end of 2 years if the interest is compounded annually, quarterly, monthly, daily, and continuously. So let's see. So what is my A0? My A0 is R is 19%, which is 0.19. T is 2. Now case 1. So A, for A, what do we have? We have N is 1. N is the number of times you're compounding in a year. Yeah, so N times per year, right? So what is the formula then going to be? We'll use this formula here. So we get, so amount at the end of it is going to be A of 2 is 1000, 1 plus 0.19 to the power n2. So this is going to be roughly $1416.10. Now, if you do quarterly, your n is 4. In that case, your A2, although I'm using the same notation, the notation, you can use a different notation for it, is going to be 1 plus 0.19. Now you're doing every year 4 times, you're doing quarterly. So quarterly means basically n is what? N is 4, right? You're doing 4 times a year. Divide by 4 times 4 times 2. And then when you simplify this, you have 1449 times $55. So you see, same interest rate, but depends on how many times you're compounding. If you're compounding frequently, at least 4 times, then you get more money than 1 times. Now let's see, if we do compounding monthly, what do you get? If n equals to 12 in this case, A12 is going to be 1 plus 0.19 divided by 12 to the power 12 times 2. And then when you simplify this, you will see that it's going to be $1457.94. Now, if you do the same thing with D, with n equals to 365, you will see that A of 2 is roughly $1462.14. And when continuous compounding, you will see that A of 2 is going to be e to the power. So 1000 times e to the power r, which is 1.9, t is 2, and you get this is going to be 1462.28. So the idea is continuous compounding gives you more with the same interest rate. So the frequency of compounding is also important, right? Now you can basically relabel this as a differential equation of the following form. dA by dt is RA.